Hey, I'm Jacob, and welcome to this instructional video on Taylor series and Taylor polynomials. So, here we have two more or less textbook definitions of what a Taylor polynomial and a Taylor series actually is. Now, feel free to copy these in your notes, but I'm going to try and explain it a little bit more clearly. Basically, a Taylor polynomial is a way to estimate a function using polynomial functions. Now, when you start off, it's not very accurate, but the more actual, the higher the degree of the polynomial, the more accurate it becomes, which leads us to Taylor series. Taylor series is actually a mathematical way to write the series that represents the Taylor polynomial out to so many spaces. Now, if you can write the Taylor polynomial out to an infinite number of spaces, then you actually model the function. The primary use for these, however, is with limited degrees, with only going out to so many powers of x in order to estimate the function without as much work. Now, there's another definition that isn't quite in here yet, and that is the Maclaurin series. A Maclaurin series is basically just a Taylor polynomial that's centered at 0. So basically what that means is that Taylor polynomials can actually be centered at any point, whereas a Maclaurin series is a very specific type of Taylor series centered at 0. So let's go ahead and take a look at some examples. Well, we're going to try and construct a Taylor polynomial. Alright, let's move on to an example, if my tablet will work. We are going to construct a Taylor polynomial for the natural log of x plus 1. And my tablet doesn't want to work. Okay, so there's one basic assumption that we have to start out with for this to work. We're assuming that the natural log of x plus 1 is equal, well, I'm sorry, is approximately our Taylor polynomial. And right now we're just going to do it out to 4. I'm sorry, that shouldn't be there. That should be over on the other side. And that's not the right tool. It should be here. Okay, so this is the basic assumption that we're starting with. Past this, we're going to expand this natural log of x plus 1 is equal to, I'm sorry, we skipped a step. We're going to center this at 0. So, technically, it is a Maclaurin series. And because we're centering it at 0, we can actually state directly that they're equal, because we're going to solve this Taylor polynomial to be equal to this. And here's how we're going to do that. Natural log of x plus 1 at 0 is equal to a sub 0 plus a sub 1 x to the 1 plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x to the 4th. Alright, now let's get a fresh piece of paper. So, because we plugged 0 in, these terms are basically all going to cancel out except for this very first one. Because anything times 0 is 0. Oops. So, all these terms are canceled out. And we're left with the natural log of 1 is equal to a sub 0. So, what is the natural log of 1? Well, it's 0, of course, so a sub 0 equals 0. And we're going to want to remember this. So if I were you, I'd write that off to the side on a scratch piece of paper. Somewhere over here, maybe. Next step. Now here is where it gets a little bit trickier. We have to find a way to find the other terms of a sub, well, first we have to find a sub 1, a sub 2, and a sub 3. So, how are we going to do this? Well, we're calculus students. We're going to derive, of course. So, we're going to do d dx of the natural log of x plus 1, substituting in, actually, I'm sorry, it is going to have to be x, because if it's not x, it's a constant, which is of course 0. Now, as you can see, when we derive this, this first term is going to cancel out. This second term is simply going to simplify to a sub 1, because we're going to carry down the 1 from up here and multiply it, and this becomes x to the 0, which is also 1. So basically we are deriving a linear function at this point, which simply just gives us the slope, a sub 1. For these other terms, as you can see, a sub 2, you're going to carry down the 2, and it's x to the 1. So a sub 2 times 2x to the 1. And the rest of these are going to follow suit. So plus 3 a sub 3 x squared, and plus 4 a sub 4 x to the 4th. I hope that still makes sense. Now, once more, oh, I'm sorry, we almost forgot one really important step, deriving natural log, which is 1 over x plus 1, or 1 over 0 plus 1, because we're plugging the 0 in, and we're just going to plug the 0 in right away, which in turn simplifies all of these out, because the zeros cancel over here, and we just have a sub 1. So, a sub 1 is equal to 1 over 0 plus 1, 1 over 1, so it's just 1. But for the sake of finding a pattern, we're going to leave it at 1 over 1. Remember, our end goal is to write a series, if at all possible, an infinite series to get the actual function. It's a lot easier to find patterns if you leave it in a fraction, because we never know quite what's going to happen with this fraction. So, let's try another. We're going to derive again we'll scribble that out. d dx of 1 over x plus 1 is going to become 1 over x plus 1 squared negative 1 over x plus 1 squared because remember this is the same thing as x plus 1 to the negative 1. The negative 1 carries out. This goes down 1, becomes squared, well negative 2 up here. And let's derive this other part. So we have this a sub 1, which is going to cancel out. This 1 is going to come down, so we're still going to have 2 a sub 2, but now it's going to be x to the 0, which is just 1, so that's no longer there. So we just have 2 a sub 2 plus 2 times 3 is 6, so 6 a sub 3 x to the 1 plus did I write 4 up here? This should have been a 3. I'm sorry. So plus 3 times 4 is 12. 12 a sub 4 x squared. Okay. For a sub 2 by plugging in 0, of course. So negative, wrong tool, negative 1 over 0 plus 1 squared equals 2 a sub 2 plus 6 a sub 3 times 0 plus 12 a sub 4 times 0 squared, which of course cancel out. All this does. So negative 1 over 1 equals 2a. Therefore, a sub 2 equals negative 1/2. That's a big deal. A sub 2 equals negative 1 over 2. Okay, I think it's time for a new sheet of paper. Okay, so what do we know so far? A sub 1 equals 1 over 1. A sub 2 equals negative 1 over 2. Probably not enough to go on yet, but let's keep going. So 1, negative 1 over x plus 1 squared equals, of course, 2a sub 2 plus 6a sub 3 x to the first plus 12a sub 4 x squared. Okay. So let's keep going and derive once more. This is the same as x plus 1 to the negative 2, which derives to, well, the 2's cancel out. I'm sorry, the negatives cancel out, and you get 2x plus 1 to the negative 3 equals, this cancels out, of course, because it's a constant. You bring this down, 6 times 1 is 1. X cancels out because it's just x, so we're looking at the slope. So 6a sub 3 plus, bring the 2 down, 24a sub 4 x to the 1. Okay. Now, let's go ahead and solve this. Plug a 0 in, 2 to the 0 plus 1 to negative 3 equals 6a sub 3 plus 24a sub 4 times 0, which of course cancels out. Let's divide, carry that 6 over, we get 1 over 3, 2, of course, 2 divided by 6 is 1/3 times 1, because 1 to the power of anything is still 1, and that is equal to a sub 3. Now let's look at what we have so far. A sub 1 is equal to 1 over 1. A sub 2 is equal to negative 1 over 2. A sub 3 is now equal to 1 over 3. Maybe we've developed a pattern. If this is a pattern, what should A sub 4 equal? I'll give you a minute to think about that. So, if A sub 1 is 1 over 1, A sub 2 is negative 1 over 2, and A sub 3 is 1 over 3, shouldn't A sub 4 be negative 1 over 4? If there's a pattern here, of course, if we're seeing the right pattern. Let's try it out. Let's derive this again. Bring the 3 down, so we have negative 6 times x plus 1 to the negative 4, negative 6, x plus that. My video cut out there. So, negative 6, x plus 1 to the negative 4th equals 24 a sub 4. Now, if we simplify this, of course, plug in a 0, 1 to the negative 4 is still just 1, so negative 6 equals 24 a sub 4. If we divide by 24, we get negative 6 over 24, which simplifies to negative, wrong tool, sorry, negative 1 over 4 equals a sub 4. So, it looks like our pattern held true. Now let's take a look at what this Taylor polynomial actually looks like. If you remember our original equation, it was p of x equals a sub 0 plus a sub 1 x plus a sub 2 x squared plus a sub 3 x cubed plus a sub 4 x to the 4th. Well, let's try plugging in these values. A sub 0, of course, was 0, so p sub x equals 1 over 1 is just 1, so x plus, x minus, because we have a negative up here, so x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. Let's take a look at what the graph of this actually looks like. Here we have the graph of x minus x squared over 2 plus x squared over 3 minus x squared over, x cubed over 3 minus x to the 4th over 4. Whew. And that's the one in blue. We don't have the other one showing yet. If we do make this other graph visible, our original function, natural log of x plus 1, we can see that they line up fairly well. Let's zoom out a little bit. Ooh, not so much there. A little worse there. Yeah, this is starting to get bad. I think you get the idea. The more numbers we add to this, the higher the degree of the Taylor polynomial, the closer this gets. So based on our current pattern, let's try and add some more. How about plus x to the 5th divided by 5. Yeah, not bad. Minus x to the 6th divided by 6. A little better. Maybe we should zoom in just so that this doesn't take too terribly long. Plus x to the 7th divided by 7. Not too shabby. Minus x to the 8th divided by 8. Look at that, we're getting a little bit closer. Plus x to the 9th divided by 9. I think you get the idea. We're getting closer and closer, but we're just not quite there. And it would take a really long time to write out an infinite number of this series. So let's take a look at Taylor series. I'm hoping you still remember our pattern. Basically, it goes 1 over 1. Wow, that was really bad. 1 over 1, negative 1 over 2, 1 over 3, negative 1 over 4. And that's what it is so far. Assuming this pattern holds, which we did in the previous section, and from the graph it looked like it was, after that we have plus 1 over 5, minus 1 over 6, plus 1 over 7, and so on. So let's try and write this as a series. Well, we should probably get our proper notation down, as I think we can probably safely start at 1, saying that a sub 0 is equal to 0. So as n equals 1, and that's to infinity, this is going to equal some number multiplied by x to the n. That number looks an awful lot like 1 over n, doesn't it? That looks pretty good. Oh, but wait. We've got one problem, don't we? We still have to handle this switching of signs. Well, that can be done easily enough. If we just put negative 1 to the n minus 1, that'll take care of our flips for us, because a negative times a negative is a positive, and a negative times a positive is a negative. So, if this is an even number, if this expression, n minus 1, evaluates to an even number, this will be even. No, if this evaluates to an even number, this will be even, which will occur on odd numbers, because it's n minus 1. So, this is positive, yep. This is negative, yep. Positive, negative, positive, negative. So this takes care of that. Normally, you write that in front, so let's just rewrite this real quick. Negative 1 to the n minus 1 to the n minus 1 times x to the n over n. And there we have it. That is our infinite series, our Taylor series, for the natural log of x plus 1. Yay! That also means that these two are equal to each other, which is nice. So just remember, if you can write a series with an infinite number of values for a Taylor polynomial, meaning the Taylor series, it exactly equals the function. If you write it to a certain number, like what we did before, this would be n equals 1 to n equals 4, then we have a Taylor polynomial, which is an estimate for the function. Go ahead and try to do the same thing for sine of x, and then for fun, try cosine of x plus pi. let's try that out and see what that does. Now, just a quick hint, all you're going to have to do for that is instead of making it a sub some number times x, you're going to make it a sub some number times x plus pi. Isn't that cool? And then all you need to do again. So this is pretty cool right here. And all you need to do is plug in negative pi instead of 0. Because then this whole expression is still going to equate to 0 and all of your terms will cancel out. Go ahead and try those problems. If you need any help, look at the examples in section 9.2 of your AP Calculus book. These two are actually right in there. They're right in that section, so you will be just fine. Now remember, this is actually for when you're centering it at a number other than 0. Got that? Other than 0. Alright. Well, good luck. Oh, and this was brought to you by Jacob's Loan.